Let's talk about some probabilities which we are using in these Markov chain or Markov process. Since we are dealing with different states, we might stay within the same state, or we might move from one state to another. So let's iterate the same point. We talk about that in the casino example, that we can play with a fair die. So fair die is one state, and then you can flip around into a loaded die. So that is another state. So you can switch between these two states. So in that case, the probability of switching is actually your transition probability. Then within that state, you can stay, and you can like throw this die like 10 times. So in that case, you are staying within the same probability, within the same state. So that has a different type of probability associated with it. So we talk about in this section what kind of probabilities are associated with this process. Transition probabilities, they represent the probability by which one event switches to another. So it's moving from one state to another. So you are using loaded die, and then you switch it into the fair one. So in that case, that is the probability with which you switch from one state to another. So if you are throwing it 10 times, and over 9 times you are using the fair one, and on 10th throw you are using the loaded one. So in that case, this transition probability is 0.1. So after like 1 out of 10 events, you switch. So if the chain is in current state Si, then it moves to state Sj at the next step with the transition probability. We represent it as Pij. And remember guys, this probability does not depend upon which state the chain was in before the current state. So now you are in current state, and now you want to switch to another state, which is the next state. So this switching from here to next state is actually depends upon your current state. So again, there is a chaining. So since you are moving from one place to another, so how you get into this point, and that doesn't matter. That was important once you are in that state, but since you are switching, you forget about the past. So the formula which denotes this probability is given by this equation. So we can put Pij, and we can use conditional probability here. We talk about that in a previous section. So we put Px of 1 which is equal to j, while x naught was I. So we can move from one state to another, while we can have the probability of this movement, which is actually a conditional probability of that present state, which is in this case here is x1, which is j, while we have already seen x naught, which is equal to I. The process can remain in one state, and it occurs with the probability of Pi and I. Sometimes, say for example, we switch to now this loaded die, and we stay there, right? So we keep on using that loaded die for some time. So how many times, if you stay within that probability, so that is your Pi and I thing. Sometimes we draw an initial probability distribution that specifies the starting state, so from where you have started your experiment. So let's look into some features of transition matrix. We know that transition probability is moving from one state to another. When we do that and we look into different, for example, in our experiment, if we have something like we are looking into transition of different nucleotides within a sequence from one position to another, in this way we can have some transition probability. So it's a square thing, and all possible states must be used both as rows and columns, and all entries between 0 and 1 inclusive, since they represent probability. So transition matrix, since it's a probability matrix, so your entries should be between 0 and 1, no negative numbers and no numbers greater than 1. And sum of entries in any row must be equal to 1, since a number in row give the probability of changing from the state at the left to one of the states indicated at the top. So let's look into this example. Here we are staying within a system where we are observing some following of the nucleotides one after another. We'll talk about CPG islands in a moment from now, where we will look into this matrix one more time. So here is how an A follows an A in this. So for example, here is an A, and we look into how many times it is followed by A in a sequence. And then how many times it's followed by C, and same way G and T. So if we sum them up here, that will be equal to 1. So same way we can do that for rest of them. So in this way we can have different situations or different probabilities, and we put them together into this transition matrix. In this section we have seen the different probabilities like transition probabilities, which are associated with Markov chain process, and the matrix that is made up of having those transition probabilities is called as the transition probability matrix. So that consists of one-step transition probabilities and in which the sum of entries in a row that corresponds to 1.